Hey everyone, welcome to an academic ZNotes live session on physics. And today we've got Kaleem Akbar with us, and we're going to talk about specific and latent heat. Let's get cracking.
Thank you very much. Welcome again, guys. Yes, we are going to do specific latent heat of fusion and vaporization, and I intend to get some exam questions done as well, just to make sure that you have got a really good understanding of, over years of experience, when I do revision classes, when it comes to thermal physics, students will go, what the hell does specific latent heat or specific heat capacity mean? So without further ado, let's get stuck right in. So we are going to deep dive this topic, and to help you understand the difference between specific heat capacity and specific latent heat, which I think is just as important, this graph will hopefully help you do this. Now, what you are looking at here is, just imagine being in a laboratory at school and you're heating up ice. Now, I remember doing this, and it bamboozled me when I was 16 years old, which was a couple of years ago. And I remember doing this in school, where you had a beaker, it was full of ice, and you put it on top of a tripod, and there was a Bunsen burner underneath. And the objective was not really to kind of measure the energy going in. The teacher was basically trying to put this point across that whilst ice was melting, the temperature would not go up. And I'm like, well, how does that work? You've got a Bunsen burner up its backside. I can see that there's a flame that's heating it. I can see that that's happening. How would the temperature not go up? Now, the experiment I'm about to describe to you is not ideal for measuring specific latent heat. It's more to show you that horizontal line that you see down the bottom right here. So this diagonal line, okay, I'll talk about it in more detail later. But these diagonal lines represent specific heat capacity, where temperature is changing. Remember from last lesson, the definition, okay, the two definitions: heat capacity, how much energy is needed to make any object go up by 1 degree Celsius, and specific heat capacity was how much energy is needed to make 1 kilogram of any object go up by 1 degree Celsius. Now, what's the difference? Specific heat capacity allows you to compare 1 kilogram of iron with 1 kilogram of aluminium, made up, right? Whereas heat capacity is more beneficial when you're looking at the same thing, really. It's hard to compare aluminium and iron because you may have different masses. It's not very helpful just using heat capacity on its own, right? But the horizontal line is the line that we're looking at today, where you can imagine a Bunsen burner heating up ice, and you've got a thermometer in that ice, and you're going to measure the temperature every 30 seconds or so. And when you record the results in a table, it's 0, it's 0, it's 0, it's still bloody 0, it's 0. And you're like, I can see a flame under there. You're looking underneath, and you're like, there's a flame. Okay, you might be tempted to bring your hand close. You're like, I can feel the heat. There's definitely something happening. Why doesn't it heat up? That is what today is all about, guys. It's the fact that the energy is being used to overcome the forces of attraction and break the bonds. You see, when a material is being heated, its energy increases. So if you imagine, whilst it's a solid, you heat it up, molecules, atoms, particles, whatever you want to call it, vibrate. That vibration is directly related to its kinetic energy, which is related to its temperature. The more it's vibrating, the higher the temperature. There comes a point where it can't vibrate anymore. And when it cannot vibrate anymore, it starts to break. And to break anything, energy is required. And that is why its temperature does not go up. The energy is being used to overcome the forces of attraction. It's breaking the bonds. Now, Latent heat of fusion is where it's breaking the bonds a little. What do I mean by that? Well, if you think about the structure of a solid, lattice-like structure, very, very strong forces of attraction, and then you've got where the molecules are kind of slipping and sliding over each other, you're kind of breaking it a little. What am I comparing it to? I'm comparing that to the latent heat of vaporization, when you are turning a liquid into a gas. That's like completely breaking something, like smashing it to pieces. All right, completely smashing it. I don't know if you're, well, like, I don't know if you've ever had a mobile phone or a PlayStation or something and it's broken, and for whatever reason, especially if you're a boy, kind of often you think that you can fix it. Right? You look at this green circuit board and you're like, yeah, I can fix that and not that. So you put it back together and let's say it works for 5 minutes, you think, how cool am I fixed that? No, you didn't. All right? Something. And if you're really, think about being a kid, you make a sandcastle. What do we do when we make sandcastles? We're hell-bent on destroying them. So solid to liquid is just breaking that sandcastle a little. Liquid to gas is that sandcastle wasn't there. That's it. And in both scenarios, in a physics sense, the temperature does not change. All right, that's very, very important to understand. Pugs, are we cool with this, or do I need to keep going?
Yep. Let's crack on.
Let's crack on. Okay. So the formula and the definition. Specific latent heat of fusion, and by the way, vaporization, the formula is the same. The definition wording changes slightly, but it's effectively the same. This means how much energy does it take to change state from a solid to a liquid, in other words, melt 1 kilogram of ice at 0 degrees Celsius. You really need to be careful with the sentence I've got there. That sentence applies to ice only. Right? And here we've got the experimental setup. So on the left side, what you see is you've got a beaker, which is quite clearly full of water, and you've got ice in a funnel. And above that, the little kind of goldy thing is a copper heater. And you can see an ammeter connected in series and a voltmeter connected in parallel. Links nicely to the electricity topic, which we've not done.
Kaleem, I'm sorry to barge in, but I don't think we're able to see your screen for some reason.
Oh, really?
Yeah.
Wow. Okay. No, something there. The whole time or just now?
I think it was when you started speaking. We didn't see the graph, so let's go over the graph a little bit. Yep, and we can see it now.
Well, that's a shame. Okay.
Yep, that's a shame. Let's just go over the graph a little bit. And
okay. Right, guys. So I had spent time talking about the invisible graph, which I expected you to see from where you're sitting. Apologies. So, guys, this is the graph showing you water being heated. All right, well, ice, which will be heated. And this little diagonal down here represents the ice. This diagonal here represents water. And if you want to imagine another diagonal, which is not going to be shown here, could be gas. So you get solid, liquid, and gas. Those are the three states of matter. Gas is not being shown here. In fact, look, just to make life clear, since you had an invisible thing to look at, let me just give you more detail. Oops. Let me see this. And there's my pen. And not the best straight line, but I want you to imagine gas, liquid, solid. Sorry for a bit of overwriting there. So whilst it's a diagonal line, you get three states of matter: solid, liquid, gas. When that's happening, think specific heat capacity. Why? There's a change in temperature. Horizontal line, first one, think melting. Second one, at the top, so let's call this 2, let's call this 1. First one, melting, specific latent heat of fusion. Second one, boiling, specific latent heat of vaporization. Why is the temperature not going up? Well, I kind of feel like all my analogies were lost now, but I hope you understand that number one, why is the temperature not going up? because all the energy is being used to overcome the forces of attraction and break apart the bonds. Same with number 2. And what you will find in reality, guys, here in a graph, number 2, let me just kind of delete part of this. Where are we? Just trying to find it. There we go. Let's just erase some of this. So let me just erase that and that. Okay. In reality, what I want to show you is that the specific latent heat of vaporization line will be longer horizontally than the specific latent heat of fusion. Now, do they really examine you on it? Not so much, but you'll see it. You will see it sometimes, okay? It depends how detailed the examiner wants to be. Very, very old papers, they tend to look the same, but in reality they're not. Why? It goes back to the sandcastle analogy. When you go from a solid to a liquid, you're breaking a liquid. When you go from a liquid to a gas, you're smashing it to smithereens. And that's the difference. You are overcoming the forces of attraction to really break it apart. All right? Yep. So the key takeaway from this slide, when we have latent heat, there is no change in temperature. Key takeaway number 2, why? Because all the energy is being used to overcome the forces of attraction. Key takeaway number 3, why does the temperature go up with specific heat capacity? It's relating to last lesson, because molecules are getting to vibrate more and more and more and more and more. Well, that means during latent heat, there is no more vibration. The kinetic energy is not increasing. It has kinetic energy, but it's not getting any more. It's now breaking. All right? If you think about a movie, when you hear earthquakes are relate a lot to movies. I like movies. Okay? Well, right now I'm watching the Karate Kid series. I never knew they had the series. It's brilliant. But when they break, like a wooden stick, or when they break the ice, why does it break? It's because it can't vibrate anymore. Its vibration is so maxed out that it's got no choice now but to break. Not that it has a choice. It's just vibrating at its maximum. It now breaks. Pugs, we cool with that?
Yep.
Cool. Let's move on now. Okay. So guys, now what I want to do is show you the experiment for specific latent heat of fusion. In other words, melting something. Okay, the actual definition for specific latent heat of fusion is the energy needed to turn 1 kilogram of a substance from a solid into a liquid without a change in temperature. But here we're talking about ice, so we're melting it. All right. Key takeaway here: students look at the 0 degrees Celsius and they think specific heat capacity. There is no change in temperature here. Yes, you can see a temperature, but it's not going to change. It's going to stay 0. We've got an electrical circuit to the top left, and this experiment was better than the one I described about the Bunsen burner earlier, because now we have a means of actually measuring the energy to melt the ice. Whereas the Bunsen burner one that I was talking about was a teacher's quick way of showing you the temperature doesn't change, but doesn't actually give you a means of measuring energy given to the ice. You're going to understand what I mean very shortly. The control experiment is vitally important. Because guys, if I've got ice in this room right now, what's going to happen to it, Pugs, without heating it up?
Sure.
What's going to happen?
Well,
just to be clear, if I just had ice and I sat it in a cup without any water in this room and left it for 10 minutes,
it would melt.
It would melt.
Yep.
Absolutely. All right. And this is the thing that students overlook. It will melt. Well, duh. Yeah, but why is that a problem for me? The problem for me when I do the experiment is I want to know how much energy I gave it, not how much energy the room gave it, because that does not help with my calculation.
Absolutely.
All right. So then we've got to take a couple of precautions. Let's reduce the amount of energy that the room gives it. Well, that's why you're picking a plastic funnel.
Yep.
Why? Because the funnel will insulate. It stops heat coming in. Okay, obviously not from the top, but we're trying to minimize the error in the experiment. Why is the ammeter and the voltmeter very useful here? Because you'll find we can measure power. How does that help me? Because energy equals power times time. You're about to see all this. Now that I've got energy equals power times time, use a stopwatch for the time. You've now got energy. If you know the mass of the ice melted, you've now got mass, and you're about to see that allows me to figure out the specific latent heat of fusion. So some made up example numbers here, guys. Ammeter 4 amps, voltmeter 12 volts. Let's say the time was 300 seconds. Okay. Water collected 90 grams. Water controlled 35 grams. What that means is if you had just left the ice in the room, 35 grams would have melted anyway. Which means my heater melted 90 minus 35. Why do I need that? Because I can tell you how much energy my heater gave the ice. I can't tell you how much energy the room gave the ice. Hope that makes sense. So now I'm going to stick in latent heat equals energy divided by mass. Can I try to break this down for you to make it simpler? Which is voltage times current times time, which is me really giving you the units. So, and then divided by the change in mass, which 4 amps times 12 volts times 300 seconds divided by 90 minus 35. Apologies, there should be brackets around the 90 minus 35 and at the top being lazy, but you get the idea, and you get 261.8 joules per gram. Notice there's no degrees Celsius here. So what that means is to turn 1 gram of ice into water, I need roughly, rounded up, 262 joules. Or if I want to change it to kilograms, let's round up, roughly 217,000 joules per kilogram to turn ice into water for this particular experiment. Hope that makes sense. Okay? So let's look at some precautions. Insulate the funnel of ice. Why? Common exam mistake. Students are so used to saying this to stop heat being lost to the surroundings. When is the last time you bought yourself an ice cream and stuck your hand on it and went, ah, that feels so hot? Never was the answer. So please make sure that, because it's such a common exam question, that, we say to stop energy being lost to the surroundings. Ice doesn't lose energy to the surroundings, it gains it. Now, obviously there's a caveat with that if you're assuming a normal room, because the normal room will be hotter than the ice. Next one. Make sure the heater is covered by the ice. Why is that really important? Well, guys, if the heater is not covered by the ice, what that means is you're actually heating up some of the air rather than all the ice. So here, energy is being lost to the surroundings. All right. One that's not been mentioned here, which would be a good one, crush the ice. Any idea why you do that, Pugs?
So that it takes lesser time, because
Okay.
like your heat's distributed to smaller, like each molecule, and then it's not spread out for entire block. Is that why?
Pugs is alluding to the right thing, guys. If you do chemistry, a larger surface area is helpful here, because if you've not crushed the ice, you've got a lot of air in between the ice, and air is an insulator, so it's going to have an impact on your results. Basically, the ultimate part, for IGCSE level, you're increasing the surface area, all right, which just speeds up the whole thing. That's the way to think about it. Next, let's look at specific latent heat of vaporization. Exact same formula, but now you're boiling the water. So the ice has went from solid to liquid, now you're going from liquid to gas. This means how much energy does it take to boil 1 kilogram of water at 100 degrees Celsius. Now again, we're talking about water here. If you're talking about a general definition, the energy needed to turn 1 kilogram of a liquid into a gas without a change in temperature. Remember, the kinetic energy is not increasing at this point, all right? All the energy is being used to overcome the forces of attraction. So let's get into the results here. Let's pretend the mass of the kettle plus water at the start is 2.5 kilograms. Let's pretend the mass at the end is 2.260 kilograms. This time you've got the power of the kettle. There's no need to figure out the current and the voltage. They gave you key and you put time. All right? So latent heat equals energy over mass. This time it's power times time divided by mass, right? Because you don't need current and voltage. So 2000, which was the power of the kettle, times the time, which is 300, divided by the change in mass, okay? So 2.50 divided minus 2.26. Plug in the numbers and you get 2.5 million joules per kilogram. Remember that graph I said to you, which was longer horizontally? Look at that number compared to the number for specific latent heat fusion of ice. So if I summarize it for you without going back, specific latent heat fusion of ice was 217,000 joules per kilogram. Here it's 2.5 million. Takes way more energy to turn a liquid into a gas than it does a solid into a liquid. Right, exam tips before we go. And let's see if you want to add this. This up to you.
No, let's go for the questions.
Imagine that. Imagine the kettle experiment. I'm going to start my timer. Would you start the timer when I start the kettle, or would you wait?
I would probably wait till we hit a steady temperature, after which it doesn't raise.
Okay, so let me simplify what Puggy just told you guys. Is absolutely right. You're after latent heat of vaporization. In other words, when it's boiling, right? You can't start your timer when you start the kettle, because what you're going to confuse here is specific heat capacity and specific latent heat of vaporization. You've got to wait till it boils. Now, before anybody gets smart, kettles turn off when they boil. I get that, but in school, we program them not to. We kind of take the button out, which can be really dangerous actually when a student takes the eye off the ball, because then all the water evaporates eventually and the kettle melts. But the point I'm trying to make is you need to wait. And it's the same for the ice experiment, by the way. You need to give the heater time to start, to heat up, to turn that ice into a liquid, because all we are interested in is the change of state. We're not interested in the diagonal. And absolutely right. Pugs, without further ado, we've been delayed a little. I'm happy to continue because you never saw the first screen. So let us now flex our muscles and do some actual past examination questions. So guys, what you're seeing here is October, November 2014 paper 3.1. And what we're looking at is figure 4.1 shows some of the apparatus that a student uses to determine specific heat capacity of aluminium. So what you're seeing is a big metal block, and there's two holes in it normally, one for the thermometer and one for the heater. And that heater externally is connected to an ammeter, a voltmeter, and you've got your stopwatch. Oh, I'm sorry, the ammeter and voltmeter is connected to a power pack, which you don't need here. And you installate the block. Okay, so state the measurements that the student needs to make, including those from the electric circuit. For each quantity, state the symbol. Well, what you need to do here is think formula. What's the formula, pardon me, for specific heat capacity? It's E equals MC delta T, or depending on the books or exam papers, E equals MC delta theta. Now let me just very quickly write that. Make this up. And there we go. So let me just write that down for you guys here. So E equals MC. I'm going to go with the exam version one. Delta theta. I don't know why Cambridge think that's easier, but they do. All right, I end up getting students confused with angles. Now remember, you can't do that as an experiment in school right now, because the only thing we can measure is mass, and we can remember the beginning temperature and the end temperature. So we can use a thermometer and we can use a mass balance, right? Now remember, find C, so C equals E over M delta theta. The issue is we cannot measure energy directly in school. So how do we do that? So over here, E equals PT. We're one step closer. We can measure time. Okay? Now, does it tell me in this question that we know power? No, we don't. It doesn't tell me that we know power. So there's another formula for power, which is IV. So here I'm good because of time. And now here I'm good because I've got current and voltage. The point I'm trying to make, guys, is when you're asked, when the examiner's asking what measurements do you need, think formula and go, right, can I actually measure it, not calculate? Energy equals power times time is a calculation. Power equals current times voltage is a calculation. How can you tell the difference? Well, if in your head or on a calculator, you're multiplying, adding, subtracting, or dividing, you're calculating. But if you're just looking at something and taking the reading from it, it's a measurement. What is it? Mass of the block, initial temperature, final temperature, time of heating, voltage, current, and is that all I need? 1, 2, 3, 4. Yeah, that's me. I've got my mass. I've got my, yeah, I've got everything that I need. So now I've got all the measurements in order for me to do that. Okay? So next, oops, I just clicked too fast. Use your symbol from A to complete the formula used to determine the specific heat capacity C. Now guys, I went overboard here. The first one in the left is what you need. Kind of done this in reverse order. That's what you need. You need voltage, you need current, you need time, you need mass, you need the final temperature and the initial temperature. The middle one is the one that you can get away with using most of the time in the exam. Look at the difference. It's the exact same as the left, except we've got PT. In other words, if we were given power, we wouldn't need the V and the I. Please, let me make it clear. The one on the left is the answer based on this question. I'm just trying to link it all together for you. We're not just answering questions here. We're trying to make sure you understand it in depth. The one in the middle is the one that you would get the most in an exam. And guys, happy birthday if you get the one in the right. Okay, because that's the simplest of all three. Understand the only thing that's changing here is the top line. All right? E, if we go from right to left, E, then PT, and then IVT is the one on the left. I hope that makes sense. And then C, sorry, part B, another student performs the experiment without using insulation. He obtains a higher value for specific heat capacity. Why is the student's measurements higher than they should be? Remember, specific heat capacity is how much energy it needs to raise one substance by 1 degree. If it's not insulated, what's going to happen by heat energy?
It's going to lose the heat.
All right? Which means you're either going to have to give it more energy, or more energy is going to be needed to make the temperature the same. Now, guys, let me give you an analogy because a lot of students don't understand this. Let's say I asked you, let's use the beach. I don't know why I'm in a summery mood. But let's say I asked you to dig a hole, right? And work with me here. 1 meter long, 1 meter wide.
All
right? So you've dug a cube out of the sand.
Yep. Yep.
And you're trying to do that when you don't realize that right behind you, I'm kicking all the sand back in. Right? Not a very nice teacher. The point I'm trying to make is you're determined to dig out sand 1 meter by 1 meter by 1 meter. Well, you get to do exactly that if I keep chucking sand back in. I hope you understand. Of course not. You're going to be digging out more sand, because I'm sticking it right back in. This is happening when energy is being lost to the surroundings. You're having to give it more energy in order to do the same thing. In other words, the specific heat capacity appears higher. How do you get around that? Insulate it better. Stop the heat being lost. Okay. Another analogy. Imagine you had a bottle of water, you're trying to fill it up with a litre, but there's a hole at the bottom. Will you stick a litre in there or more? Of course it's going to be more, because some of the water is leaking. All right, I hope that makes sense. Some of these things are hard to imagine without analogies. I don't want you to start writing about sand and stuff in the exam. You're not going to get any marks. Don't write about bottles with holes coming out of them. It's to help you get what's happening. It's to help you understand what that is saying. Right. I believe this is our last example. It's a latent heat example. So let's go ahead and do it. A mass of 0.36 kilograms of a certain substance in a solid state in a well-insulated container. The substance is heated at a rate of 1.2 times 10 to the 4 joules per minute. 2 minutes after starting the heating, sorry, I've got plugs in the way of this, I'm just moving plugs. The substance is all at the same temperature and it starts to melt. 11 minutes after starting the heating, the substance finishes melting and the temperature starts to rise again. Calculate the specific heat of the substance. I want to point out something here that is a bit naughty. I would love to ask the audience at home, if you would answer, if they're watching, how many of you think they're referring to water? How many of you think they're referring to ice? I bet quite a few. Here's the issue. You talk about ice and water here, you're going to lose marks, because they said certain substance. See, the issue we have in school is we do easy experiments. Nobody's going to ask you about the melting point of mercury, are they? You're not going to get to do it because it's poisonous in liquid form, right? So you've got to be careful sometimes that, sorry, when I say poisonous, toxic, that you don't just talk about what you're always used to. So how do we calculate the specific latent heat of the substance? See, they haven't even told you what it is. So let's just go here. Several times, what's going on? There we go. So remember, latent heat equals energy over mass. But I'm going to break this down into two little parts. Let's do energy equals power times time. You have got, technically, the power, and you go, how have I got the power? Power is measured in watts. Well, remember, power is energy divided by time.
Yep.
What you get 1.2 times 10 to the 4 joules per minute. That is effectively power, but it's not measured in watts. So what you want to do here is you want to do E equals PT, which is 1.2 times 10 to the 4. And the nice thing is, a lot of students would say, okay, let's change this into joules. You don't have to. Why? Because everything is joules or minutes. Now you could, because that's what a lot of students are taught to do, but it won't be helpful here alone. You're just making it harder. So it's 1.2 times 10 to the 4 times 9 minutes. Now where the hell did I get that from? We started at 2 minutes. We finished at 11. 11 minus 2, 9. So what do I get? So I've got 108,000. Okay, I wouldn't even give this units because I've not changed it to seconds, so I can't really call it. No, in fact, I can call it joules because it's joules per minute. Yeah, it's fine. So 108,000 joules. Then I'm going to do latent heat equals energy divided by mass. Stick that energy in, divided by the mass, and 3 times 10 to the 5 joules per kilogram. Notice there is no degrees Celsius in here because you're changing state. After 11 minutes of heating, when the temperature starts rising again, in which state is the substance? Now remember, we turned it from a solid into a liquid. Which state is the substance after it's melted? Well, surely it's liquid. And notice even the mark scheme says, ignore vapor, gas, or water. Right? Well, first of all, vapor and gas is wrong. and ignore water because you didn't even know it was heat to begin with. Okay, so vindicated in that answer. And then finally, describe what happens to the molecules as thermal energy is supplied to them in this state. Now remember, whilst it is solid, it vibrates. Whilst it's melting, there is no more vibration. The energy is used to overcome the forces of attraction. Now you've turned into a liquid. What's going to happen? The kinetic energy increases again. All right? So basically it's going to move around more rapidly. Why? Because it's flipping and sliding now. All right? Ignore starts to vibrate. It was already vibrating. There's just going to be more vibration. We've overcome forces of attraction. Remember, we've changed state. We're now a liquid. And you could talk about convection currents because it's a liquid. And what happens in liquid? Energy is rising. Sorry. So hot fluid rises, cold fluid falls. But the key to understand is it's not a liquid. Molecules will slip and slide. They'll start to move faster. Don't talk about molecules expanding. Molecules don't expand. The substance expands. All right. That middle answer there, guys, you could say any one of the appropriate things. You don't need to say all. So when you see / this or this or this or this, and when they stick not in block capitals, basically means not this, not this, not this, not this. I hope that makes sense. Okay? Yep. What time for another one? It looks like there's another question here. Or are you happy with what we've done?
Well, I mean, it's up to you. If you want to keep going, we could certainly.
Why not? Let's crack on. Let's make this the last one, right?
Yep.
Define the specific heat capacity of a substance. Oops, that shouldn't be there. Okay. Yep. The energy needed to raise 1 kilogram of a substance by 1 degree Celsius. That is the specific heat capacity of a. So let's ignore what's written. Okay, ignore that completely. All right. Figure 4.1. Let's see if I can just. Oops. Figure 4.1.
Yep, it's the same experiment that we've been looking at.
Absolutely. Shows a cylinder of aluminium heated by an electric heater. The mass of the cylinder is 800 grams. The heater delivers 8,000 joules of thermal energy to the cylinder, and the temperature of the cylinder increases by 12. This question looks a lot kinder. So what's going to happen here? Calculate the value of the specific heat capacity of aluminium. This is what I mean by happy birthday. All right? No power needed, no current, voltage, etc. They gave you the energy, they gave you the mass, they gave you the change in temperature effectively. So specific heat equals energy over mass times change in temperature. 8,700 over 800 times 12. I mean, if you get this in the exam, happy birthday to you. All right? 0.91 joules per kilogram, joules per gram degree Celsius, or 910 joules per kilogram degree Celsius. Now, look, if you can fit in grams, you can leave the answer in grams. Okay, they're just showing you can use both. No big deal. That was actually a lot easier than I thought. Okay, and the formula is there. Calculate the thermal capacity of the aluminium. Now that's different. Thermal capacity involves no kilogram. Okay, it's not specific heat capacity involves kilogram. Thermal capacity doesn't. So thermal capacity is basically energy, quite often in Mark schemes written as Q, divided by change in temperature. Here is delta T, sometimes written as delta theta. So we've already got the numbers. So it's 8,700 divided by 12. All right. All the or, which basically gives us 730 joules per degrees Celsius. Okay, so it's just 8,700 divided by 12, which gives us 730 joules per degrees Celsius. The difference between specific heat capacity and heat capacity, we just drop the kilogram. I hope that makes sense at home, guys. Look, I think that is us almost towards the end. Stay and explain up for improving the accuracy of this experiment. As Pug was saying, very similar to the first one. We don't want to use any heat to the surroundings. let's add insulation. Okay, insulate it in any way, shape, or form, add a lid, etc., etc.
Yep.
Okay. There's loads of different. Yeah, it boils down to the same thing. Right. For me, that is it. I don't think we've got time for any other questions. What about your audience, Purge? Do they have any questions that you might want to ask? Or
let's give them a moment. So if you guys have any questions, you can drop it in the comment section. We'll have a look at it. Right. So that's it for today, and we'll wrap it up. For updates, you can join our Discord community, follow us on Instagram, or just subscribe to the YouTube channel. All the resources that we used for this session are in the description below. So be sure to check it out. That's it for today.
Thank you very much, Rob. Thank you.
Thank you, guys.